The solar storm can scramble signals above Earth and push currents through long wires below, yet most people never notice. Now imagine the next storm arrives after Earth has lost much of the invisible system that normally organizes that encounter. The first question is not, is this instant apocalypse? It is, which parts of modern life get stress-tested first? Earth's magnetic field is often imagined as a planetary force field. Turn it off, and danger pours straight in. That is too simple. The field helps shape the magnetosphere, the region around Earth that changes how charged particles in the solar wind approach the planet. Think of it as an outer traffic pattern. It is not a solid wall. It does not stop every particle, and conditions are not identical everywhere. But it helps organize the flow before particles interact with Earth's electrically active upper atmosphere. If that global field weakened greatly or disappeared, solar wind particles could interact more directly with the ionosphere and upper atmosphere. That is a real change. It is not, by itself, evidence for instant atmospheric loss, a known radiation crisis at ground level, or one universal global failure, and the change might not look like a light switch. During irregular magnetic reversals, compass directions can vary for centuries. The field may become weak, patchy, and changeable, rather than simply going from fully on to fully off. So here is the more useful test. What changes on a quiet day? And what changes when the Sunday stops being quiet? Start with the calm version. No major solar disturbance. No warning siren from the Sunday. Even today, Earth's magnetic field is not a perfectly uniform bubble. At the surface, models put its total strength at roughly 22 to 67 microteslas, depending on location, elevation, crustal effects, and changing geomagnetic conditions. With much less global field, the clearest immediate difference is overhead. Charged solar particles would interact more directly with the ionosphere and upper atmosphere. That puts the systems nearest the environment at the exposed edge of the problem. Think less about a person standing outside with an umbrella, and more about an astronaut outside while the weather changes. Spacecraft, people in orbit, and aircraft at high altitude are closer to where the conditions shift. A quiet Sunday does not mean nothing happens. It means the vulnerability is there, but not yet under its hardest test. Space weather has calm periods, active periods, and major storms. The storm is where the thought experiment gets serious. When a solar particle event or a severe solar storm arrives, satellites and astronauts are among the clearest concerns. Without a strong intrinsic field, spacecraft and astronauts would face greater exposure to charged particles, especially during energetic events. Satellites can also face broader space weather effects, including risks to electronics and changes that affect how they operate in orbit. But there is no honest single number for that danger. One satellite is not in the same situation as another. Orbit matters, altitude matters, shielding matters. So does the intensity of the solar event, whether Earth's field is somewhat weakened or completely absent. The same logic applies to high-altitude aviation. During severe events, flights at high altitude can face greater radiation and space weather risk. That does not mean every flight instantly becomes unsafe. It means exposure depends on the particular route, altitude, aircraft, and storm. That is the key idea. Earth's field is not a magic shield with one failure setting. It is part of a changing relationship. A situation that is manageable during quiet conditions can become far more demanding during a major solar event. The next effect is less visible, but much closer to everyday life. The ionosphere is a region high in the atmosphere containing electrically charged particles. During geomagnetic storms, conditions there can change. Those changes are associated with radio navigation errors and other operational disruptions. So a disturbance far above Earth can interfere with systems that depend on signals passing through or interacting with that upper layer of the atmosphere. Navigation and radio services may become less reliable right when operators need reliable information most. Space weather has an unfortunate sense of timing. A greatly weakened magnetic field could substantially change how solar disturbances couple to near-Earth systems. But that does not mean every effect simply gets stronger by the same amount. The solar wind matters. The remaining ionosphere matters. So do the degree and shape of the field loss. It is less like turning up one volume knob and more like rearranging the sound system while the concert is already playing. Some signals may change in ways that field strength alone cannot neatly predict. And a solar storm does not have to stay in orbit or in the upper atmosphere. Even with Earth's current magnetic field, geomagnetic storms can produce geomagnetically induced currents in long-conducting systems. They can also bring ionospheric changes, satellite drag, radio navigation errors, and risks to spacecraft electronics. Long conductors matter because they connect distant places. Electrical infrastructure spans huge distances, and changing magnetic conditions can induce currents in those systems. That is one path by which activity driven by the Sunday becomes an engineering problem on the ground. Would a weakened field guarantee more blackouts? The evidence does not support that claim. What it does support is more specific. During solar disturbances, vulnerabilities involving long conductors, spacecraft electronics, and some radio or navigation systems could change substantially. Exactly how would depend on the solar wind and the remaining ionosphere. That may sound less cinematic than a guaranteed worldwide outage. It is also more useful. Engineers do not prepare for a vague apocalypse. They prepare for unstable signals, altered operating conditions, induced currents, and equipment exposed during severe space weather. There is one effect people could notice without a satellite dish, a power line, or a flight plan, a compass. If the field became weak, unstable, or entered an irregular reversal, magnetic direction could become confusing. A compass does not know where geographic north is. It aligns with the magnetic environment around it. During an irregular reversal, that direction can vary for centuries. So the familiar image of every compass needle snapping neatly from north to south is misleading. A reversal is better understood as a long, messy reorganization of directions. Magnetic compasses would no longer offer a stable global direction reference for people and systems that use them directly. That is a practical reminder that the field matters even on a quiet day. Humans would not be the only navigators dealing with altered cues. Some animals use magnetic information for orientation and migration. A major field change could disrupt species that rely on magnetic direction, inclination, or intensity. But many also use sunlight, stars, landmarks, odors, ocean currents, and other clues. The consequences would vary sharply by species, not follow one universal biological script. At this point, it is tempting to leap to the biggest conclusion. No magnetic field means Earth loses its atmosphere. The supplied evidence does not justify that shortcut. A weaker field would allow more direct interaction between solar particles than the upper atmosphere, and over long timescales that could matter for atmospheric escape. But research comparing Mars, Venus, Earth, and induced magnetospheres shows that atmospheric retention depends on many factors. It cannot be reduced to whether a planet has an internally generated magnetic dipole. That is not a loophole. It is the scientific complication. A planet does not hold on to or lose an atmosphere because of one component alone. Magnetic field strength by itself cannot tell us how Earth's atmosphere would respond across immense spans of time. The same discipline applies to human habitability. The clearest supported near-term concerns are operational. Spacecraft and astronauts, high-altitude aviation, satellites, radio navigation, and long-conducting systems. And a definitive claim that Earth instantly becomes unlivable. Which brings us back to the opening storm. On a quiet day, a greatly weakened magnetic field would mainly change how charged solar particles interact with Earth's upper environment. The most immediate, well-supported concerns would be overhead, spacecraft, astronauts, and high-altitude operations. Then a solar disturbance arrives, and the pressure test gets harder. Radiation and space weather exposure can rise for systems in orbit and at altitude. Ionospheric changes can disrupt radio navigation. Long conductors and spacecraft electronics may face altered risks, but there is no single damage total waiting at the end of that chain. The outcome depends on the Sunday's activity, how much field remains, the state of the ionosphere, and where each exposed system happens to be. A quiet day, a moderate storm, and a severe solar event are not steps on one inevitable disaster curve. They are different conditions acting on a complex planet. So Earth's magnetic field is not a magic wall between us and the Sunday. It is part of the traffic system that shapes the encounter. If it weakened greatly, the practical question would not be, when does the apocalypse start? It would be, when the next solar storm arrives, which systems are exposed, how ready are we to keep them working?